Okay, so the topic for today is torsion, as you can see on the screen. So let's have a bit of an introduction. The concepts here and equations are pretty similar to your linear forces. It's just translated into rotational movement. So you'll see later. So torsion. So before we start, the reason why we're studying torsion is because in many engineering applications, members are required to carry torsional loads. And we consider for torsion, the most efficient shape for that to resist torsional loads is a circular shaft. That's why most of the problems that we'll be solving for involve circular shafts, okay? So the derivation of equations for the analysis of torsion, consider the following. So first is your simplifying equations. So here's an example of your circular shaft, okay? So the assumption is line AB deforms into the helix AB prime as the free end rotates through angle theta. So usually what happens during torsional load is you have a fixed end, then one end is free to move. So for example, at this end, you apply this torsion T, okay? So line AB, A is fixed, then B moves to B prime. That's what happens. And when that happens, and it rotates through an angle theta, as you can see, represented by this, that's the angle with which the points at this end move. And then the cross section do not deform. So even though this whole thing rotates, it has uniform cross section still. Or not uniform, however, at each section, it's the same before and after rotation. Also, length L of the shaft remains constant here. Total length, and then actual normal strain is 0. So again, when we're considering torsion, we're not going to consider actual strain created by that torsion anymore. The assumption is that actual strain is 0. Since strain is change in length over length, if there's no change in length, so strain is 0. Okay? Then each cross-section rotates as a rigid entity about the axis of the shaft. So in short, there's no deformation to consider here if everything moves as a rigid body. Remember, rigid body meaning resisting deformation. Okay. Next assumption that we'll have is compatibility. Okay. So look at the figure. So this figure on top first. So consider a portion of your shaft, hence this. As the shaft deforms, the two cross sections of the segment rotate about the x-axis. So this is a portion of your full shaft. So this side and the side at the back rotates about an x-axis. So it's this axis right here. And considering again all the assumptions earlier, we get this equation. Shear stress. We talked about shear stress in our topic strain. So shear stress equals d theta over dx times rho. So let's figure out how did we get those equations. Okay. I've already written it out. So recall from your geometry, right? Arc length equals r radius of your circle times angle of which your arc subtends. So looking at this drawing, okay, this is your arc. Right? Your d moves through this distance, this arc towards d theta. Therefore, this is your s from d to d theta. R is this line, denoted by rho, and angle between them is d theta. Okay. So the reason why it's d theta because it's a very small angle of twist, right? Differential theta. You remember differential calculus. So again, S R theta. Therefore, if you create an equation, then d theta equals rho d theta. And another thing, looking at the other side of your figure, right? Again, this is still your S d theta. R can be considered this length. Sorry about that, which is actually, again, for differential length x, because you're just considering a small portion, a differential segment from the total length of your shaft, hence dx, right? Small segment. And then within this dx, this angle is now called your delta. Okay? So considering this side is the theta, considering this side, the angle of twist is delta. So again, S equals r theta. So here r is delta, then, sorry, your r is dx, your theta is delta. So putting that into equation, we have that. Therefore, remember, delta is the deformation, strain, shear strain. So shear strain, remember by definition, is the displacement of angle for the side of your object. So that is what this represents. Also, looking at your figure. So this line deformed to this line. Same thing with your shear stress in your previous discussions. Knowing that, let's solve for that. Delta is now equal to, just considering this equation, d theta, divide both sides by dx, so d theta over dx times rho. Now that we have that, considering torsion, recall in our previous lecture again, shear stress equals shear strain times modulus of rigidity. But we have a new equation for shear strain. So sub that in here. So therefore, a new equation for shear stress is now G modulus of rigidity times d theta over dx times rho. Again, rho is the radius of your cross section of your shaft. d theta is the angle of twist. Then dx is the differential segment of your shaft. That is where this equation came from. So yan, d theta over dx now is angle of twist per unit length. Then shear stress varies linearly with the radial distance rho from the axis of the shaft. So here at the center of the shaft, shear stress is minimal at the center. If you can imagine rotating a shaft, the deformation at the center doesn't really move much. What deforms the most is at the edges, right? So that's what it means by varying linearly. The stress increases at a constant rate from center to edge. And then maximum shear stress, therefore, is at the surface of the shaft. That's why we're only considering stress at the outer edge, because that's the maximum. That is the most critical stress that we have. And remember, when designing, we're using the critical stresses. The stresses that are first to fail. Okay, next. Next thing to consider are your equilibrium equations. So for the shaft to be in equilibrium, the resultant shear stress acting on cross-section must be equal to the internal torque acting on the cross-section. So that's the equation for your torque. So even though your shaft is rotating, it's still maintaining your equilibrium. Okay. Again, let's create an equation. Let's derive that equation. So when you rotate the shaft, it's experiencing shear stress. Okay, the movement of your shaft is being resisted by its internal torque, T. That's capital T. So to solve for that, let's consider again what is shear stress. Remember, one of our first equations, first lectures, shear stress is just simply shear force over area, right? So this your V over A, that's shear force over area. But since we're considering a small segment, that's why this differential force over the differential area. Because the shear strain on a shaft is not uniform. That's why we're considering small segments first. So now that we have that, dV therefore equals shear stress times differential area. And recall, we have an equation for this, for shear stress, which is this. G d theta dx rho. Sub that into our equation. We have this. And times dA. Now, again, we're looking for internal torque. Remember, torque just has this equation T equals Rf. So in the differential terms, remember R is rho for your shaft, and then force is your shear force, so V. That's why this rho V. Now to get the total torque, since this is differential, just apply integral calculus to get the summation of this. Okay. And bring your calculus. So now we get the integral of rho dV. And then rho dV is just tau dA, and it's just g d theta dx rho dA. So T is now equal to this. Rho times rho, you get rho squared. So this is now your equation. And here is where we'll introduce your polar moment of inertia. So from your previous mechanics topic, polar moment of inertia is a measure of a beam's ability to resist torsion. Okay. So it has the equation J equals integral of rho squared dA. So subbing that into our equation, we get this. Okay. J equals rho squared dA, sub that here. We're gonna get torque equals G d theta over dx, and rho squared dA is just simply J. Okay? Next, multiply both sides by dx, and then divide both sides by G and J. You're gonna get, this side is left with d theta equals T times dx over jg. And then, to remove the differential, remember, just apply integral calculus, get the integral of both sides. Integral of d theta is just theta. Okay, so recall integral of dx is just x, right? Whatever that variable is. So here it's theta. And then integral of T torque over jg dx. So this torque, resistance is constant. Polar moment of inertia of an object is also constant. Same with modulus of rigidity, it's constant. So all of this can be factored out. So you're going to be left with integral of dx. And as I've said earlier, integral of dx is just x. So that is just x from 0 to L, right? And that is just L minus 0, right? Therefore, this is just T times L over jg. So that is where that equation came from. So theta now is just TL over jg. Okay. You understand? Any questions? If you understand, please answer yes or no. Okay, good. Next. So the first part is more on just deriving your equation so you know where everything came from. Okay. Next. Well, now we have a summary of all your torsion formulas. You have your shear stress, maximum stress, and polar moment of inertia and maximum shear stress for solid shaft, and then your hollow shaft. So again, let's figure out how do we get that? Here. Okay. So combining the equations that we gotten earlier, your shear stress and torque. Okay. You have your torque and then shear stress. Okay. So equation 1 and 2, combining those two equations, you get, as you can see, T is g d theta over dx, g d theta over dx is T over J. So sub that here, this becomes T over J, so T over J times rho, shear stress. So now you have a new equation. So that is your basic equation for shear stress. Torque times radius over polar moment of inertia. Now, let's figure out what is polar moment of inertia, a review from your previous mechanics classes. You've tackled this before, right? So, as a review, polar moment of inertia is just integral of rho squared dA. Rho squared, if we're considering a circular shaft, okay, that is x and y. We have x and y axis. Okay, again, If you have circular cross section, this is your rho, therefore this is x, this is y. Okay? Therefore rho, Categorian theorem is just x squared plus y squared dA. Separating that integral of x squared dA plus integral of y squared dA, that is just your moment of inertia about the x-axis, and then this is moment of inertia about y-axis. Polar moment of inertia is also just the summation of moment of inertia along the x and y-axis. Now, for our problems, usually we're going to be considered with solid shafts and hollow shafts. That's why we've memorized this equation. Okay, the moment of inertia for a solid shaft along the x and y is the same. It's just pi d to the fourth over 64. Okay. So summing that into our equation for polar moment of inertia, ix plus iy, since it's equal, this is just times 2, or add each other. So pi d squared, pi d to the 4th over 64 plus pi d to the 4th over 64, you're going to get pi d to the 4th over 32. So this is polar moment of inertia for solid shaft. Next, your maximum shear stress. Remember from our earlier equation, shear stress is T rho over J. So subbing that in, so T, the same rho, for a solid shaft is just diameter over 2, right? That's your radius, then over J. And J for a solid shaft is pi d to the 4th over 32. So sub that there, D cancels out, 32 and 2, you're gonna get 16T over pi d cubed, right? Yeah. Those are your equations. Any questions for torsion formulas for solid shaft? Okay. Next. So we're gonna do the same for hollow shaft. So the only difference between solid and hollow is the diameter. So here, instead of just d to the fourth, it's d to the fourth minus d to the fourth, outer diameter minus inner diameter, since this is a hollow shaft. So yun lang. And the last of our equations, okay, so one common application of shafts is to transmit power. That's why we have an equation for that. Torque equals power over 2 pi f. And again, how did we get that? So recall what's the equation for power? Can anybody give me equation for power? Anybody remember? Remember not this. This is already for torsion. What was the equation for power for linear motion? Not FD, Coulomb. Correct Marco and Rod. FD over T or work over T. Mendoza. Okay. So yes, power is work over time. The work is just force times distance over time. Or distance over time is your velocity. So force times velocity. This for linear motion. Translating that to rotational, force is torsion. Linear velocity, angular velocity. Okay, so this is torque. Yeah, this is torsion. This is angular velocity. Okay, remember from your physics classes, angular velocity is just 2 pi f. Hence, P is just and your torque or torsion rather, torsion equals power over 2 pi f. Okay, so that is where that came from, right? Do you understand before we move on to our examples? Please answer yes or no. And if you have any questions, just ask me. Again, if you understand, please answer yes or no. Okay, let's have an example. Number 1. The figure shows a 2-inch diameter solid steel cylinder that is built into the support at C and subjected to the torques TA and TB. Letter A, determine the maximum shear stresses in segments AB and BC if the cylinder, and B, compute the angle of rotation of NA. Use G equals 12 times 10 raised to 6 psi for steel. Okay. So we're looking for maximum stress and angle of rotation. I've already written out the solution. Okay, so first step, as usual, write your given. Next, draw your free body diagram. So the steps are pretty similar to your other solutions. Okay, you just fix the settings of this. So sign convention, let's talk about that first. So you have this drawing. Okay, let's say this is counterclockwise, this is clockwise. So drawing that counterclockwise, clockwise. Okay, so we can solve this as is. The first step is to get the internal forces, since the equations for our solution requires your internal force, your torsional resistance. Okay, we need to look for T. So the same steps apply. Cut your segment, figure out the internal force. So for here, what I did is I figured out the reaction here. You can solve this without looking for the reaction. So what you do is, I've drawn the FVD. Since I want to know this, again, you can solve this without, but let's try solving with it. To solve for it, you're going to use summation of moment. Obviously, since we're always going to deal with rotational motion here, we can't use summation of forces vertical and horizontal. Okay? Summation of moment equals 0. Now, how do I use sign convention? So, I can't really show it, okay? But do you remember your right-hand rule for physics? Right? So, try to do it. You're gonna curl your fingers in the direction of your force. Okay. Then your thumb, if your thumb is pointing towards your segment, that is negative. It's pointing away from the segment, then it's positive. Okay? So, let's see. Now, opposite. If your thumb points towards the segment, that's positive, away from the segment, negative. So similar to your compression, if it's towards your object or segment, compression, so negative. If it's away, it's tension, therefore positive. So that's our sign convention. In other books, it's the opposite, okay? So don't be confused, the sign convention is arbitrary, meaning not set in stone. So let me write that here. Try to imagine. Okay? So let's say these are your fingers, this is your thumb. If it's pointing towards your segment, it's a tip. Okay? So for example, that is for a force that is this way. Okay? If you're kailangan 3D. Let's do this 3D. Okay? Next. So curling your fingers. The thumb will be that way, away. So that is your negative. It gets your fingers will follow how the direction of your torque is applied. This way towards your segment, positive. Here, away from your towards your segment, negative. Away from your segment, positive. Right. Let's do it here. Okay. So applying right hand rule. Right hand rule, always use the right hand. So here, so 900 would be positive, right? Since if you curl your fingers here, your finger will be pointing away. Next, for B, that would be negative since you're pointing towards the segment. Okay. So now that I know P is negative, negative just means if you curl your fingers, it's gonna be pointing towards your segment. Yeah, that's how I drew it. So after figuring out your reaction, segment. So let's start with this. So cut your segment here. You have this, you have your reaction. So this is your internal torsion. Summation of moment equals 0 still. So summation of m equals 0. Therefore, PBC is negative. We've already figured that out. And then negative TBC. Then to counter that, this should be in the opposite direction. So plus TBC, negative 500 plus TBC equals 0. Therefore, TBC equals 500 pounds foot. And the sign of that is positive. Again, since we figured out P here is negative, to counter that, this should be positive. Okay. Next, considering section AB, again, cut a segment. This is 900. That is, if you use right hand rule, 900 would be, looking at the drawing, positive. Okay. Positive since away from your segment. Then to counter that, this should be countering that movement. It's going to be away from the segment as well. So it's also positive. Okay. Next. So again, that's just summation of moment equals 0. So TAB equals 900 pounds foot. So that's positive. After solving for T, you can now use your equation for shear stress, maximum shear stress 16T over pi d cubed. So now it's just a matter of direct substitution. So 16T for BC is 500. So 16 times 500. Our unit are in pound foot, right? That's the given. But our G is in PSI. So I need to convert that. So pound foot, foot to inches. Yeah. So 1 foot has 12 inches. Yeah. So that's why 16 times 500 times 12. Then over pi d cubed. D is given 2 inches diameter. So it's in inches, so no need to convert, right? Solving for that, you get 3819.72 psi. Next, do the same thing for AB. Again, 16t over pi d cubed, so 16 times 900 times 12, again, to convert your feet to inches. Then over pi d cubed. So D is the same, still 2. Solving for that, you get 6875.49 psi. So that's first part. Next, letter B, solving for theta. So theta is just going to be, since you have two segments here, it's just going to be the summation of the rotation of both of your segments. Okay? So sign convention is important here, because that's going to tell you if they're going to be added or subtracted. Okay? Since here we figured out they're both positive, therefore their angle of twist will just be in summation. So in short, summation, to get total angle of twist is just summation of TL over JG. So JG is the same for both segments, right? Since the material and dimensions are the same. That's why everything is over JG. So now TL is what's different. So TAB times LAB plus TBC times LBC. Okay? Then just sub in your values. TAB, again, we've solved for to be positive 900. 900 times length of your member, let's see, 5 feet. Again, our G is in inches, so times 5 times 12. Okay. Also, our torque is in feet again, so that's why there's another 12 here. Okay. So 900-pound foot times 12 to inches times 5 feet for length. Again, times 12 to convert to inches. Then do the same thing for BC, so plus BC is 500-pound foot times 12 for inches times length. This is 5, this is 3 for BC, as you can see. So 3 times 12 for inches. And over, polar moment of inertia of this segment is a hollow shaft. So remember, that's just pi d to the 4th over 32. polar moment of inertia of a hollow shaft. Let's see. ID to the fourth over 32. And D is given to be 2 inches. That's why this is 2 raised to 4 over 32. And then lastly, your G, which is given, which is 12 times 6 PS, times 10 raised to 6 PSI. Okay? So solving for this, you're gonna get 0.05 radians. But most of the time, the final answer should be in degrees. Okay? So after computing for 0.05 rad, convert to degrees, so that's just multiplied by 180 over pi. The final answer is 2.63 degrees. Okay? Again, theta, the answer here will always be in radians. Then convert it to degrees. The final answer is 2.63. Okay, any questions for number 1? Do you understand number 1 then? Please answer yes or no. Okay, good. Gets naman sign convention. Okay. You can just use right hand rule. Okay. As a review, this would be away. This would be towards. Then your torque. Okay. Since away is positive, towards is negative. Ako pala yung una kong sign convention. My bad. Okay. So 900 is away, so positive. 400 is towards, so negative. So solving for T, it's positive. So it's going to be away from your shaft. So this would be away from your shaft. If you imagine that is counterclockwise direction, okay? If you look at this 3D, and then the reaction here would be counterclockwise as well. So if you use right hand rule, this would be away from the shaft. Your thumb will be pointing away from the shaft. So that's why this is positive. Same thing here. Okay. If you draw this, your thumb is going to be away from the shaft, following the direction of 900. Therefore, the reaction here would also be away from the shaft. If you draw it, this would be counterclockwise. This would be clockwise. So again, away from the shaft. So right hand rule governs the sign convention of your equation or of your values. Okay, so try to do it on your own, the right hand rule. Okay, done with number one, let's move on to number two. The shaft in the figure consists of a 3-inch diameter aluminum segment that is rigidly joined to a 2-inch diameter steel segment. The ends of the shafts are attached to two rigid supports. Calculate the maximum shear stress developed in each segment when the torque P equals 10 kip-inch is applied. Use G equals 4 times 10 raised to 6 psi for aluminum and G equals 12 times 10 raised to 6 psi for steel. So this is similar to your indeterminate members, right? Both ends are not free to move. Both ends are restricted. Hence, you'll be using compatibility equations to make up for the lack of equations for 8. Again, first step is to write out your given. First, and diameter of aluminum 3 inches, of steel 2 inches. Next, torque applied is 10 kip-inch. So that is kilopounds inch. This is just times 10 raised to 3 or times 1,000 to get pound inch. Okay. Next, G of aluminum is 4, and then for steel it's 12. And then draw your free body diagram. And find that. So you have your torque applied here. It is counterclockwise if you're looking at it from this way. Counterclockwise. So therefore, the reactions would be to oppose that. So the reactions at both ends would be clockwise. So hence clockwise, clockwise. So this is counter, this is clockwise. Okay. Next step would be to create your equilibrium equation. So summation of moment equals 0. So clockwise, positive, counterclockwise, negative. It's the usual sign convention for your moments. So positive TAL, negative T, positive TST equals 0. So TAL plus TST is just equal to T, which is 10 pound inch, a kilopound inch. So times 10 raised to 3 for this to be pound inches. Okay? So that's your equation 1. I have two unknowns, TAL, TST. To get another equation, you're going to use your compatibility. So your whole system is attached to rigid supports. Then your torque is applied here. Hence, okay, the angle of twist of both sides, your steel and aluminum, would be the same, right? Since the same torque is applied and they're attached, so they're going to rotate the same way or the same amount. So therefore, angle of twist of aluminum equals angle of twist of steel. So that is your compatibility equation. So just write out the equation, TL over JG for aluminum, TL over JG for steel. So TAL, length of your aluminum is 6 feet. Again, everything in inches, so times 12 over JG. So J is pi d to the 4th over 32. This is still a solid shaft. Yeah. And diameter of aluminum is 3. So therefore, this is 3 raised to 4. And modulus of rigidity of aluminum is 4. So 4 times 3 is 6. Equals, yeah, TST times length of your steel, 3 feet, convert to inches, so times 12 over JG. So J is pi d to the 4th over 32. G is 12 times 10 raised to 6. Two equations, two unknowns. You can solve for TAL and TST. And again, what are we looking for? Maximum shear stress developed in each segment. Now I know the torsion in each member. So T. So to get shear stress, tau, just sub in T to the equation. Okay. So tau equals 16T over pi d cubed. Again, this maximum shear stress for a solid shaft. So subbing in your value, 16 times TAL, 4576.27 over pi d cubed. Again, diameter of aluminum is 3. So you get 863.21 psi And then for steel, same thing, 16 times T over pi d cubed. So 16 times T for steel, which is 5423.73 over pi d cubed. Diameter of steel is 2, hence 2. So our final answer is 3452.85 psi for steel. Okay, that's number 2. Do you have any questions? None? Okay. If you don't have any questions, and if you understand, please answer yes or no. Okay, good. Next, moving on to number 3. The 4 rigid gears loaded as shown in the figure are attached to a 2-inch diameter steel shaft. Compute the angle of rotation of gear A relative to gear D. Again, you have your gears. We want to know angle of rotation of A relative to D. Since this isn't attached to any rigid support, therefore all of them will rotate depending on their internal forces. So we want to know the total of A compared to D. Let's start. Okay, so the solution is pretty straightforward. To get the total rotation of A compared to D, we're just going to look for the rotation of segment BC or AB, BC, and CD and take the summation of that, or the algebraic sum of that. Okay? So therefore, the first step is to figure out the internal forces. Right out they're given, diameter, these are all the same, I believe. Yeah, all of them have 2-inch diameter shafts. We're looking for internal forces in the shaft. And then G is 12 times 10 raised to 6. Okay, so once again, we're going to segment and then solve for the internal forces. Let's start with AB. So this is your AB. Applied force is counterclockwise, 500. This is counterclockwise, 500. Counter that has to be clockwise, AB. And summation of moment equals 0. Okay, and then we need to know, so you're going to get counterclockwise, so using right hand rule on this end. So using it counterclockwise here, it's going to be pointing away from your shaft. And then here, clockwise. So if you're going to hold it clockwise, it's going to be pointing away from your shaft as well. Summation of moment equals 0. Therefore, TAB equals 500. Positive since away from the shaft. Again, using right hand rule on here. Okay, next. Segment BC. Or A to C. So segment A to C, getting a segment on this end. So we're going to have clockwise 900 pound-foot application. Again, I'm looking counterclockwise and clockwise through this end. This is counter, this is clockwise, right? So 900, 500. So clockwise 900, counterclockwise 500. To counter that TBC, you're going to make an intelligent guess so that this is in equilibrium. I need another counterclockwise force so that this is equal to 0. So hence, I drew this counterclockwise TBC. Summation of moment equals 0. Okay. Next, therefore, TBC equals outlier sign convention. So, ganito na lang. Para hindi nakakalito. You're just gonna apply the sign convention at the end. Okay, to know if your force is positive or negative. Then in solving, just use clockwise or counterclockwise. Okay? So clockwise positive, counterclockwise negative. Ganun na lang. Okay, so TBC equals 900 is clockwise, therefore positive, 500 is counterclockwise, therefore negative. The answer is 400. Then the sign of TBC using right hand rule. Okay, if you use your right hand here, your thumb will be pointing away from the segment. Mm-hmm. This is counterclockwise. If you use your right hand rule, your thumb will be pointing towards the segment. Therefore, that is negative. Okay? Yun na lang. Sa dulo na lang natin gagawin yung right hand rule. And then lastly, from A to D, so counterclockwise 500, clockwise 900, counterclockwise 1000. Drawing that, clockwise 500, counter 500, clockwise 900, counter 1000. And then, to counter that, your TCD should be, again, making an intelligent guess, the summation of moment equals 0, so TCD equals so following what I said, counterclockwise negative, so negative 1000, positive 900, negative 500. The value of this, the magnitude would be 600. But the sign would be negative. Again, we're not going to follow the sign of that. Instead, we're going to use the right hand rule to get the sign. So this is just to get the magnitude. Okay? So magnitude 600, then use your right hand rule to figure out the sign. So this is clockwise. Using your right hand rule on this, your thumb will be pointing away from your segment, therefore positive. So now you have TAB positive, TBC negative, TCD positive. Okay? So looking here, our solution is the same summation of TL over JG equals TAB LAB, since this is the same material. So JG is the same, hence everything JG. So again, TAB LAB plus TBC LBC plus TCD LCB. Sub in your values. TAB is 500 pound-foot. So again, our G is in PSI. So convert foot to inches, so times 12, times length of member AB, A to B. So that's 5 feet. So 5, again, convert to inches, so times 12. Next, plus, your TBC is negative, so negative 400 pound-foot times 12 for inches. Then length of B to C, segment B to C is 3 feet. Times 3, convert to inches, times 12. And then lastly, for members CB, internal force is 600 pound-foot times 12, and again, lastly, length is 4 feet times 12. Then over polar moment, pi d to the fourth over 34. D is given to be 2 inches, then G is 12 times 10 raised to 6. Solving for this, you're gonna get 0.03 radians. And again, the answer you get here would be in radians. We want it in degrees, so times 180 over pi to convert to degrees. Final answer, 1.62. Okay? Any questions? Number 3. None? You understand number 3? Please answer yes, sir. Okay, next. Second to the last, I believe. Yep. Number 4. The figure shows a steel shaft of length 1.5 meters and diameter 25 millimeters that carries a distributed torque of intensity, meaning torque per unit length of T, which is equal to T sub B, which is equal to X over L. Sorry, P equals TB times X over L. Or TB is 200 Newton meter per meter. Determine letter A, the maximum shear stress in the shaft, and B, the angle of twist in the shaft. Use G as ATGPA for steel. So now we don't have a uniform applied torque. Instead, we have uniformly distributed torque with varying intensity. So, since this is varying, we need integral calculus to get the total torque. Okay, start. First, write your given length 1.5, diameter 25, then your torque 200 Newton meter per meter. So Newton meter is your usual unit for torque, but since this is distribution, that's why it's still over meter pa rin. Okay? So this is not just newtons. This means torque per meter. Then times G equals ATGPA. Okay. So to solve for this, we need to get the summation of this torque from 0 to L throughout the entire length of your shaft. So in short, to get your total torsional resistance, you're gonna get the integral of your torque about dx from length 0 to L. Okay? Since remember, torque equals RF. And R is the distance of point of application from axis. So here, our R now is actually the length. Okay? Point of application from axis. That's why this is my equation, and then just get the summation since our given force is this. Okay? And then T is equal to this 200, it's equal to TB times X over L. Sub that in TB times X over L dx. PB over L is constant since the value of PB is the same. Okay, it's 200. Also, total length of your shaft is constant as well. So after that out, so you're left with integral of x dx. And using integral calculus, integral of x is just x squared over 2. So integrate x squared over 2 from 0 to L. So just subbing L in 0, you get PBL over 2 minus PB times 0 over 2. So that cancels out. So you're left with PBL over 2. And then just sub in your values. PB is 200. L is 1.5. These are all in meters, so uniform units, then over 2. So you get 200 times 1.5 over 2, 150 Newton meter. So this 150 Newton meter is the actual total torque being experienced by your shaft. So that's not what's being asked. We're asking maximum shear stress. So since this is a uniform shaft, okay, and the total torque is already solved for 150, all we need to do now is just to sub that into our equation. So remember, maximum shear stress is 16P over pi b cubed. That's equal to 16 times your P 150 Newton meter. Then let's see, how are these in GPA? So 80 times 10 raised to 3 MPa. So you want our units to be Newton millimeter. So Newton is the same, so just convert this to millimeter, so that is 1 meter equals 1000 millimeters. And over pi d cubed. So pi d is already in millimeters, so no need to convert 25 cubed. Solving for this, you get 48.89 MPa. Okay, next, letter B. Angle of twist of the shaft. And as you can see, since this is a distributed load or distributed torque, angle of twist would be the summation of all the angles of twist each force creates on your shaft. That's why, as you can see, this is again your integral calculus. Okay, we're looking for angle of twist. So angle of twist has the equation PL over JG. So I need first to know what is P, right? So this P, I can't use that since that is used for the total force experienced by your shaft. I can only use it in maximum shear. Okay. So instead, let's create an equation for torque at a certain point in your rod. So let's say I want to know the torque at this area. So let's call that distance x from your support. Okay. Therefore, when you take the summation of moment here, summation of moment equals 0, that would be equal to, so you have your total torque P, right? And then there's still your distributed torque, small t. So let's call that P times dx, like what we did here. That's the distributed load. And then you have your reaction PA, reaction at the support. Therefore, summation of moment in direction ito, counterclockwise. So your distributed load is counterclockwise, therefore your reaction should be clockwise. Yeah. So summation of moment equals 0. This is clockwise, therefore positive. Next, this denotes your summation of torque at this point. So minus, so integral of t dx from 0 to x. Again, this is representing your torque at a distance from your support. Okay. Then minus t, this is the maximum torque or total torque being experienced by your shaft. And equals 0. So this is what we're looking for, P. Okay. And P. I needed an equation form. So therefore, isolating P is now equal to PA minus integral of t dx. And then just sub in PA. You already know PA is equal to PBL over 2. I wrote it as TBL squared over 2L for now because I need to show you how your two equations will combine. As you can see, this is actually TBL squared over 2L. 2L cancels out, that's why this is just TBL over 2. But in actual, that is TBL squared over 2L. Okay? TBL squared over 2L minus integral of this, so integral of 0 to x of t. Again, t is just given to be TB times x over L. TB times x over L, dx. Okay? So do the same thing here as you did in letter A. So integral of t dxl over dx. So factoring out t, b, and l, since those are constant, then integral of x dx is just x squared over 2. X squared over 2. But now instead of 0 to L, it's from 0 to a distance x from your support. Okay? Therefore, this becomes tb x squared over 2L. So tbl squared over 2L minus tbx squared over 2L, you get same denominator. So it's just tb L squared minus TB x squared. Factor out TB, you get TB times L squared minus x squared. Okay? So now I have this equation for torque being experienced by your shaft. I'll use this equation to find out the total angle of twist. Okay? And again, our angle of twist is not constant, so we're going to use an integral calculus. So angle of twist equals TL over JG. Now our L, we're going to consider a differential length dx, not the total length anymore. Remember, in our derivation, the way we got our equation is to consider a small segment. So same thing with theta, let's consider a small segment dx. Okay? So instead of TL over JG, you get TDX over JG. And again, we're going to integrate from 0 to total length L. Next, sub in your T. So T is equal to this equation, TBL squared minus x squared over 2L. Okay, then over JG. TB and L, and TB and 2L are constant, remember? Therefore, I can factor all of those out. So you get TB over 2L. And of course, JG is also constant since this is the same shaft. Uniform shape of your shaft as well. So J is constant. So I'm left with integral of L squared minus x squared dx from 0 to L. So just apply your integration. Integral of L squared dx. L squared will be considered a constant. So this just integral of L squared dx would be L squared times x. And minus integral of x squared is just x cubed over 3 from 0 to L. So just sub in L and 0 here. So you're going to be left with TB over 2LJG times L squared times L is L cubed minus L cubed over 3. So L cubed minus L cubed over 3 is equal to 2/3 L cubed. Okay? That's why this is now 2/3 L cubed. Cancel out 2, cancel out L. Finally, you get this equation, TBL squared over 3J. Now I have all of these values. I can finally sub in 200 for TB times 1.5 for L, 1.5 meters, 1.5 meters squared, and then conversion. Our units are in Newton millimeter squared, so I need to convert that. So 200 Newton meter per meter, that's essentially just Newton, so I don't need to convert 200. So that's still 200. Next, 1.5 squared meter, convert to millimeter, so that's times 1,000. But since this is squared, this is also squared. Okay? Then over 3JG. So 3, then J is pi d to the 4th over 32. So pi, diameter is given to be 25 millimeters. 25 raised to 4 over 32. And then times G. G is 80 times 10 raised to 3 MPa. Then finally, you get 0.05 radians. Again, convert to degrees, so times 180 over pi, you get 2.80 degrees. Any questions for number 4? None? Do you understand number 4 then? Please answer yes, sir. Okay, how about the others? Do you have any questions? Okay, good. So since we're almost out of time, okay, I'm gonna solve this next meeting instead. It's gonna be a short solution. And then we'll move on to the next topic, which is flange ball coupling connection. Okay? And then, meeting pa rin naman ata sa Saturday, right? On Saturday, you're gonna have your quiz number 3, your last quiz. Topic is everything I've discussed for module 3, so that would be thermal stress, and then here, torsion, and then flange ball coupling. Alright? Do you have any questions before I dismiss you? Yes? Okay, completion, I'm gonna be posting another exam for you to answer. Just wait for that this week. Di ko pa napopost. I'm gonna make an announcement about it soon. So for modules 1 and 2, you can complete it anytime within the term, since the final submission of grades would be on the 11th week, I believe. Okay. So for those who submitted your project, let me know. Send me a message, okay? I'm gonna be checking that again this week as well to fix your module 2 grade. Okay. Because it doesn't notify me if someone resubmitted an assignment or a project. You're welcome. Any other concerns? Project Reviewer 3 would be due on the 3rd week for this module, so week 11. So week 11, Wednesday. Kailan yun? Week 10 na ngayon, di ba? So, February 17 is the due date of your project. Any other concerns? So again, on Saturday is your quiz. Wala kayong homework. Okay, I'll just give you the 5% for homework. Because if you fail in module 3, there's no more completion for that. You have to retake it the next term. So my goal is walang mag-IP sa module 3. Okay? So please, yung mga IP ng module 1 and 2, do your completion work. Okay? Para, remember, 2 IPs, matic 5. Okay? Wala nang concerns. Alright. Since you don't have any more concerns, you may go. Goodbye, class.
Yeah, ma'am.